Hello everyone, thank you for attending this morning's webinar on loudspeaker testing. My name is James Kelly. I'm the Regional Support Manager at Audio Precision and Grass Sound and Vibration, and I'm based here in the UK. I've worked for Audio Precision for over 11 years in sales and application support, and transitioned to a full-time support position for Audio Precision and Grass in January of this year. Prior to working for Audio Precision, I worked in audio electronics, producing automated test solutions, mostly for hi-fi and pro audio companies, since the mid-80s. So let's get started. Our agenda this morning, we're going to take a high-level look at these agenda items because 1 hour isn't really enough to go into detail on even one single aspect of the agenda. But we're going to look at free field measurements, acoustic response, quasi-anechoic techniques and the time window, combining near field and far field data, impedance till small measurements, loudspeaker production test, and rub and buzz. So free field measurements. Acoustic loudspeaker measurements should be conducted in a free field, and a free field is a region in space around a sound source where sound may propagate freely in all directions with no obstructions. If a loudspeaker and a microphone are in a free field, the microphone will measure only the direct sound radiated from the loudspeaker. This is obviously desirable. We want to measure the sound radiated from the loudspeaker itself to have data that is representative of the loudspeaker, independent of the environment in which it is located. An idealized example of this is a point source, an object that is small compared to the wavelength of sound radiating from it. And that's indicated by the image on the left. Located high above the ground, away from any reflective surfaces. When an idealized point source radiates sound in a free field, the sound intensity is inversely proportional to the square of the distance from the source. Sound intensity is proportional to sound pressure squared. Hence, the sound pressure level decreases by 6 dB per doubling of the distance from the source. This phenomenon is sometimes called the inverse square law, or 6 dB double distance rule. So, conducting free field measurements, and in all honesty, you've really got two choices: outdoors or an anechoic chamber. And free field measurements are most commonly conducted in an anechoic chamber. Conducting free field measurements outdoors is challenging due to loudspeaker and microphone placement and additional complications caused by inclement weather, especially if you live in the UK, and ambient noise from wind, traffic, etc. An anechoic chamber is a special room lined with highly absorptive material on its interior surfaces, walls, ceiling, floor and doors, as shown in the image. To improve absorption at lower frequencies, the material is formed into wedges with the wedge tips facing into the room. In fully anechoic chambers, an acoustically transparent working surface above the floor wedges is usually provided by means of an open steel wire mesh suspended from the walls. An anechoic chamber approximates a free field above a lower limiting frequency, determined mainly by the length of its wedges. This lower frequency limit can be estimated from another rule of thumb. To absorb sound of a given frequency, the significant dimension of the absorptive material must be at least 1/4 of the wavelength. Based on the quarter wavelength rule and the speed of sound in air at room temperature, 1 meter long wedges can effectively absorb sound above approximately 86 Hz in frequency. For practical reasons and cost, it is rare to find an anechoic chamber with a lower limiting frequency below 60 to 80 Hz. You can see on the slide a graphical representation of an anechoic chamber which is suspended. And this helps isolation from any road noise or from the building itself. Our next image is a hemianechoic chamber where perhaps the room could be used for something else, and when needed, a mat of wedges can be placed in the room for anechoic measurements. Acoustic response measurement. So in APX 500 software, the acoustic response provides up to 20 measurement results, including impulse response and energy time curve. The impulse response and energy time curve provide a graphical control of the time window. And basically this means you can pick up the time window on the graph itself and move it to gate out any seen reflections either in the impulse response or the energy time curve. Along with this, we get obviously RMS level, relative level, deviation result, delay, phase, group delay, level and distortion, THD, ratio and level, distortion product, ratio and level, rub and buzz, both crest factor and peak ratio, and zone track residual, zone track rub and buzz, frequency shift if it's open loop, and the acquired waveform. Now, acquired waveform is really useful when measuring systems with a delay. You might be measuring a Bluetooth loudspeaker, for example, and compensating for the delay to make sure you capture the whole log chirp. The acquired waveform is very useful for representing that. In addition to this, the rub and buzz results require a software option. So with the traditional APX analyzers, such as 525, 555, 585, and 515, you'll need a loudspeaker software option, either loudspeaker production test or loudspeaker R&D. For the 517 and Flex, you might opt for a Flex pack that includes these measurements and gives you these results in acoustic response. I should point out that for the 517 and the Flex, loudspeaker production test is a standard measurement and will provide rub and buzz results. It's just whether you need these in acoustic response or not that you would opt for that option. Excuse me while I have a drink. So when presenting acoustic response data, an anechoic response is implied. So the data that you loudspeaker manufacturers produce will always be anechoic. And we'll be looking at some tools as to how we can help provide that, even if we don't have the best environment. From our RMS response, we can specify the speaker sensitivity, and this is normally specified at 1 watt, 1 meter. Now, this is for the nominal rated impedance. So we have a calculation where V is a square root of power times resistance or impedance. And for example, 1 watt, 8 ohms gives a voltage of 2.83 volts RMS. And quite often you'll see loudspeaker sensitivity specified at 2.83 volts rather than at 1 watt, 1 meter. And this is usually down to the fact that the nominal impedance may not be equal to the DC resistance or the actual impedance. So you might get a loudspeaker that has a driver sensitivity and its nominal impedance, let's say, is 8 ohms, but when you measure impedance, it might actually be nearer to 6. These measurements can be made at different levels and refer to 1 watt at 1 meter. So measurements in ordinary rooms are obviously contaminated by reflections. And we have obviously some options, some that we've discussed. Anechoic chamber is ideal. Outdoors, as we've discussed, is problematic, but if you get the right environment, is very good for free field measurements. And then we have our quasi-anechoic techniques, time selective measurements using the time window, and a combination of these techniques to produce a free field response for a loudspeaker. So if we look at the time selective techniques, our traditional far field measurement is based on a calculation where the maximum dimension of a loudspeaker, represented here by the M, and the far field has to be greater than 3 times that dimension. You can then calculate the time when you should receive the first reflection based on the distance, the microphone, and the distance to the nearest reflecting surface. And you can see that calculation on the screen now. And that's represented by T. And you can see T represented on the graph for the impulse response. And this should be sufficient to gate out any reflections. You can see it on the impulse response or alternatively on the energy time curve. Now, gating out reflections is great, but it does have some effect on low frequency response. And you can see in the graph bottom right of the screen that if the time window is set to 1 second, you get a different response than you do when it's set to 5 milliseconds. And it effectively adds smoothing and also an area within the response graph, which is obviously contaminated by reflections. So one method to overcome this is, for the low frequency part of the free field response, is to do a near field measurement. For this, we want to put the microphone as close as possible to the low frequency driver. This eliminates reflection and noise, valid at low frequency because the driver behaves like a rigid piston. And here you can see a graph representing the response of the low frequency section of a loudspeaker, and then on the right there's a theoretical upper frequency for near field measurements versus the major dimension M that we referenced in the last slide. So we can achieve our near field measurement. We have our far field measurement, and to get an overall response, we need to combine the two. Now, APX has a very nice utility called the splice utility, which you can download and use for your measurements, and it will combine the two. This will only show the relative frequency response. So it doesn't give you an overall RMS level response, but this will be relative to a chosen frequency within the overlap region. So moving on, impedance teal small. Another important set of results and parameters for loudspeaker measurements. Used as the rated quantity for drivers and speaker system. Usually the drive level is small enough to ensure operation in a linear region, and it's the basis for determining teal small parameters. In APX software, we usually have a couple of options for measuring impedance. You can measure the voltage across the sense resistor only, or for better results, more accurate results, you can measure voltage across the driver and the voltage across the sense resistor for improved accuracy and full teal small parameters. You can see we have a impedance phase response at the bottom right of the screen, and impedance magnitude, where you can see the resonant frequency of the drive unit, which is the peak in that response. Teal small parameters are electromechanical parameters that define low frequency driver performance. Published specs used to help designers of cabinets and crossovers. Small signal parameters are usually measured and reported. Mechanical components are non-linear, so this means these results will change with temperature and over time. And yeah, if you've been using a loudspeaker for many hours, then you'll get different results than if you've been using it new out of the box. So APX provides teal small parameters with the impedance response and based on 3 different models, and the models are electromechanical resonance system, and we have a standard model, an LR2 model, and a Wright model. The till small parameters should be derived from the best fit of model to the impedance curve. So you can see on the top right hand corner the fit, and in blue the actual impedance, and you'll see a list of till small results below this, including the resonant frequency of the driver, which, as we mentioned, will be at this peak, QMS, QES, total Q, etc., and all of these results can be used either with a loudspeaker design software, or is also very useful when looking for replacement drive units, perhaps due to obsolescence. So advanced till small parameters requires a second sweep. Well, actually, not all of them require a second sweep, but we've got our models, as we discussed. Standard model usually provides a good fit at lower frequency. LR2 and Wright models a better fit at high frequency, and the LR2 will provide populated results in the till small parameters for R2, L2, and ERM, EXM, KXM will be populated with the Wright model. Now, the way to achieve these full till small parameters, most commonly used, would be added mass. So this requires a second sweep. So what you do is you do a sweep in free air, and then usually add some mass, can be in the form of a toroid, usually using something like blue tack or modeling clay, and can be put as a toroid around the dust cap. So you need to add enough mass so that you shift the resonant frequency by at least 5%. An APX will accept mass in the range of 1 gram to 1,000 grams. And there you see a representation of the original impedance and fit, and then with the added mass, and then the fit for the added mass sweep. Another method is to use a known volume. So the driver can be mounted on a sealed enclosure, and if the driver is facing into the enclosure, you need to calculate the total volume by adding the volume of the enclosure to the volume of the truncated conic section formed by the driver cone. If the driver is mounted inside a sealed enclosure facing out, you then obviously have to subtract the volume of the driver cone, frame and magnet assembly from the volume of the enclosure. Mounting the driver on a sealed enclosure will shift its resonant frequency, peak in the impedance curve, upward by reducing the compliance of the system. The smaller the enclosure, the more the resonant frequency is shifted. You must reduce the compliance enough to shift the resonant frequency by at least 5%, similar to when using added mass. Then we have known moving mass. So rather than making 2 measurements for till small as described previously, you can enter the moving mass of the driver without air load and derive a full set of parameters in one sweep. The moving mass should be available from a manufacturer's specification or can be obtained by disassembling an identical driver and weighing the moving parts. And if you enter the no moving mass into the MMD field in APX, you can achieve full till small parameters. So till small. Now let's have a look at loudspeaker production test. So loudspeaker production test is provided, as I said, as standard on 517 and Flex, and is an option in the other AP analyzers. And this really is a measurement, as it suggests, for production of loudspeakers or loudspeaker drive units. And you'll see many of the results are similar to acoustic response. You have an RMS level, a relative level. You do get an impulse response. You get phase response, level and distortion. Similar to acoustic response, we get THD ratio, THD level, distortion product, ratio and level. And we get a number of rub and buzz results. And the rub and buzz results actually in loudspeaker production test are more comprehensive than they are in acoustic response. We also get impedance response, impedance magnitude, and impedance phase response. And we get partial till small parameters. In addition to this, we get the acquired waveform, but we also have the reference waveform and cross correlation between the two. Now, the reason loudspeaker production test has a more comprehensive list of rub and buzz results is because we have a choice of stimulus. We can use a log chirp, same as we use in acoustic response, or we can use a fast sweep. A fast sweep is a very fast stepped frequency sweep. As I said, we get additional rub and buzz results, including rub and buzz loudness and high order harmonic distortion. The time window is controlled by a time window field where you enter the value of where you would like the time window. It doesn't have a graphical representation in the impulse response that you can click on and move graphically. So you need to type this in. And a word of warning when typing in a value into the time window control field. Unlike almost any other field in the APX software, because the time window can be specified in distance, such as feet and meters, if you're specifying the time window in seconds, you must type the S. So in this image, you can see it's 100 milliseconds. So if you're changing this, don't just type in 50M for 50 milliseconds, because you'll end up at 50 meters. Impedance till small, as I mentioned, you get impedance magnitude, impedance phase, and till small partial results. And you have the options as you would in the impedance till small measurements for measuring either just the sense resistor or the driver and the voltage across the sense resistor, and your different models. And you don't get a second sweep because you don't get full till small parameters in the loudspeaker production test, but it provides a very quick single sweep, whether it's log chirp or fast sweep, of providing till small results. So the fast sweep, as I mentioned, is a super fast step frequency sweep. Has no input or output ranging between steps, continuous transition between steps to minimize transient effects, and the total sweep time can rival the speed of a log chirp. And anyone who's used step frequency sweeps and would like, let's say, a fairly high resolution, you will know how long those old step frequency sweeps take, and the new fast sweep is much faster. Not quite as fast as log chirp for the resolution, but it also has some advantages and avoids some of the limitations of chirp. So there's no transient ripples at low or high frequency. You can sweep from low to high or high to low. You're able to measure harmonics above the 20th harmonic, which is great for the high order harmonics. It says required here. You can still get high order harmonic distortion as a result from the log chirp, but it will be limited to the 20th harmonic. Returns only the data points you need instead of thousands. So your stepped frequencies, which you can specify, or you can choose, let's say, from an ISO series and 24th octave, for example, it will only return those values. And it can provide a stationary signal required for rub and buzz loudness. And we'll be moving on to rub and buzz, and you'll understand, hopefully, why that's a great breakthrough for APX and the loudspeaker production test. So, rub and buzz. What is rub and buzz? It's any of several manufacturing defects which result in undesirable noise being emitted during speaker operation. So this includes, obviously, rub, and this could be where the cone is off center, canted, and mechanically rubs when it moves. Could be buzz, often referred to as crap in the gap, but these are particles such as chipped magnet material or loose strings of glue trapped between the voice coil and the gap. And air leaks, perforations in the surround, or imperfectly sealed dust caps. Usually, but not always, the rub and buzz is harmonically related to the fundamental. And of course, it could be something completely outside of the speaker. It could be a car door panel, for example, sympathetically rattling, or something loose in the enclosure, especially with modern loudspeakers that might be part of a system. You might have a switch on a device, whether it's a smart speaker, let's say a sound bar with buttons and connectors, and it could be something like that that's rattling. So why is rub and buzz difficult to measure? It's a subjective problem. So there's no real universal agreement as to what is too much. Different sounds are perceived as more or less annoying by different people. All speakers have a lot of distortion. So compared to electronic devices, the THD curve of a typical speaker is already difficult to read and relate to quality. And production test is usually carried out in a difficult environment. Customers want to test for rub and buzz in an environment that is already very noisy. Frequency response and distortion measurements will only detect the most severe cases of rub and buzz. And this is because rub and buzz is a small signal. It might be more than 50 dB below the fundamental. So in measurements, it is swamped by the fundamental and the second and third harmonics. Unfortunately, the human hearing is very good at detecting these small signals. They tend to be at high frequency, so background noise doesn't mask them, and they tend to have a very high order harmonic structure, so frequency masking doesn't conceal them either. There are various techniques that attempt to unmask these artifacts and make it possible to reliably test for rub and buzz on a production line. So, with the launch of version 6.1 of the APX 500 software, we now have a very comprehensive package of rub and buzz detectors. We have rub and buzz, which we've had for a while. This uses a high pass tracking filter that removes the fundamental and also the low order harmonics. Detects defects as excursions in the residual waveform crest factor or peak ratio. And if you've been using APX 500 software, you may well be aware of that traditional rub and buzz that we've had for a while. So in addition to that, we now have SoundTrack. This is a third-party developed improvement to rub and buzz. It filters the residual signal and the ratio to the RMS of the total signal in order to reduce the noise of the result. We then have high order harmonic distortion. This is a classic method, and if anyone had ever seen a seminar that I presented back, I think in 2017, this was actually mentioned and shown how you could do this using distortion product ratio with a log chirp. But as mentioned, it's limited to the 20th harmonic with a log chirp. But using the fast sweep, you can basically tune the high order harmonic distortion, and if wanted, you could have the 20th harmonic to the 200th harmonic, and is a good way to account for frequency masking effects. And then we have rub and buzz loudness. This calculates the psychoacoustic effect of the distortion signal based on well understood models of human perception of sound. And this is possibly the most representative detector of that annoying sound that we hear when there is rub and buzz artifacts. So here we have some examples of rub and buzz. Top left is peak ratio, and the blue trace is loose particles between the coil and the gap. The green trace is backplate interference, and then the orange trace is a loudspeaker without any rub and buzz. Then similar results, top right, which is SoundTrack, and you can see here how the resulting graph is cleaned up, less noisy. Then bottom left, we have our high order harmonics, where I would say it would be almost impossible to detect the loose particles, but you would still be able to detect them, the backplate interference. And then bottom right, we have rub and buzz loudness. And here you can quite easily see that this has a definite difference, both for the loose particles and the backplate interference. So we'll be relatively simple to set limits around this and pick up both defects. So summary of how the rub and buzz for peak ratio and crest factor, which we've had for a while, works. We have our log chirp, and we have this sliding high pass filter, which tracks the chirp frequency and has a time multiplier, U typically of times 20 or times 30. And this results in a residual peak and a residual RMS. And we also get the main RMS from the original acquired waveform. Crest factor is the residual peak over the residual RMS, and then the peak ratio is the residual peak over the main RMS. High crest factor and high peak ratio would normally indicate a defect. As previously mentioned, we then have our zone track, which, as you can see once again on the graph, reduces the noise in the result, and this can make it much easier for detecting rub and buzz artifacts. Has built-in decimation, so you can choose your octave decimation, and it has an RMS or peak detection mode. High order harmonic distortion. It's just THD, but only including the high order distortion products. Most rub and buzz mechanisms produce a rich spectrum of distortion products. Excluding the low order harmonics is a simple approximation of the frequency masking effects of human hearing. And this is a classic solution to rub and buzz, first used in the 90s and still a very popular solution. And this is, as I've mentioned, high order harmonic is available with log chirp. You will get results, but it is only supported up to the 20th harmonic. So high order harmonic distortion is best used with a fast sweep, as you get much higher harmonic included in the result. And then rub and buzz loudness. And as we mentioned, it applies a modern stationary loudness model to the noise and distortion. And the model accounts for biological masking effects, e.g. blood flow in the inner ear, the Zwicker loudness model, frequency masking effects, and it's normalized to the fundamental amplitude. Provides an absolute estimate of the loudness of the rub and buzz, and it's the simplest to interpret. Limits are usually a simple flat threshold and are often universal in the range of 25 to 50 FONs. The rub and buzz loudness is only available with a fast sweep stimulus. So moving on, measurement equipment. So there are standards for loudspeaker measurements, and the IEC 60268-1 specifies that a microphone with a known calibration should be used. The recommended practice for free field measurement conditions is to use a free field measurement microphone. And here we have the 46AE as an example. These calibrated microphones are stable and have a flat frequency response over a wide frequency range. For greater precision, if needed, the APX audio analyzers has an input equalization feature, which can be used to eliminate any deviations from flatness from the measured response. So typically with a free field measurement microphone, it will be provided with data, including a response curve of the microphone. So if you wanted to, you could use that to EQ any deviation from flatness. The standard also specifies that the signal generator, power amplifier used to drive the loudspeaker, and the microphone system have a flat frequency response within plus or minus 0.5 of a dB. All of our analyzers easily meet this requirement, including the 517 with its own instrument grade amplifier. There is a note here that in section 8 of the IEC 60268-5 indicates that a pressure microphone should be used. This is a holdover from a much earlier time when the frequency response correction of a free field microphone was uncertain. Current recommended practice to use a free field microphone for free field measurements, as we mentioned. So I'm going to be making some measurements on a loudspeaker, and what I'm using here is the APX 517 as shown on the slide. I'll be driving a loudspeaker from the power amplifier output, and I'll be measuring this on a measurement microphone connected to the mic input using constant current power supply, so a pre-polarized measurement microphone. And these are placed inside the Grass AL30 acoustic measurement chamber. And these are great for production test of acoustic devices in a production environment. I'm actually in a relatively quiet office, but yeah, these are great for use on a production floor. I have my 517 powered up and connected, and just for sanity, what I will do, got my measurement microphone connected. I'm going to calibrate this from TEDS. I'm going to read TEDS and set the sensitivity. I'm in acoustic mode, and I've then set acoustic mode in this signal path for the output. Now I'm going to set the acoustic output level. There we have 80 dB SPL. And I'll turn that off. Now, first of all, let's have a look at acoustic response. Our loudspeaker that I'm using is specified 150 Hertz, I think, to 20K. I'm actually doing a sweep up to 15K, doing a 1 second sweep at 94 dB SPL. So here we have our time window control. I'll leave the start as automatic, and our window end is at 550 milliseconds. Now, this is the graphical representation that I mentioned, where you can graphically control the time window. And you can do this on the impulse response or the energy time curve while the data is live. One thing I would like to point out, and you'll be able to see this in the film strip at the bottom. So here we have our RMS level response of the loudspeaker, and you can see there's no grey area on there due to our positioning of the time window. But if we had reflections that we wanted to gate out, see if I can get this close enough to, there you go. So on the film strip, you can now see we have this area. You can see the effect of the time window on the low frequency response. And this is as we discussed in the slides. So dependent on the environment, dependent where your first reflections are, this could be a case for carrying out near field and far field and splicing the two together. Here now you can see these results. Deviation, this is the change in level across the whole bandwidth. I can change these values. Let's try. There. You can see in this range we have much less deviation. This is, as you can see in the response graph. Delay, which can be measured in time or in distance. Phase response. Using one channel, we've got our group delay, level and distortion. We got our THD ratio. We have a couple of calculation modes now, which in most cases make very little difference. And we now have the option to normalize the THD. Same for we have THD level, distortion product ratio, and again we have the calculation mode, and we can look at individual harmonics, or we can have a look at the sum of the harmonics. And for example, we could turn off these low order harmonics and effectively get a high order harmonic distortion result represented there. This is a similar method to how the high order harmonics would work for a log chirp. Also get our distortion product level with similar results, but expressed as a level. Rub and buzz, where we have crest factor and peak ratio. Then we have subsequent graphs with just the crest factor, just the peak ratio. Then have our soundtrack residual and our soundtrack rub and buzz. And this could be we have different detectors as mentioned and different decimations you can do on third octave, 24th octave and any of the others. Frequency shift is only applicable when carrying out open loop measurements. And this is when you might generate the chirp from an external source. And then the acquired waveform. As I mentioned, if you were measuring something like a Bluetooth loudspeaker, this is a great representation to ensure you capture the complete chirp. So let's have a look at loudspeaker production test. So as I said, lots of similar results. Let's change this to 15K as well, so we get something that's easier to compare. Here we've got our RMS level response, relative level, phase response, and then, as we've just been through, level and distortion, THD ratio, THD level. Let's have a look at some of these. So here we have the impulse response, and we can see our time window control is set to 100 milliseconds. But this is not represented on the impulse response graph. It's one of the differences, because you don't have this graphical control of the time window. So one of the big differences, and as I mentioned, we say to 10. If I don't put that S in, we're 10 meters on the time window and not 10 milliseconds. There, and we'll still get the grey areas on the, say, on the RMS level response. Let's change this to something. And there you see, so you still get the representation on the results graphs and how it affects all of these results, but you don't have that graphical control where you can pick it up on any of the results. So it's still not there on the impulse response. We get our high order harmonic distortion, and even though this says maximum harmonic, we know that if we're using a log chirp, we can only go up to the 20th harmonic. We get our rub and buzz results as per acoustic response, but we also get the high order harmonics and the rub and, we don't get rub and buzz loudness on log chirp, but we will on fast sweep. But we also get our impedance response, impedance phase, and we get our partial till small parameters. So we know that the resonant frequency of this speaker is around 250 Hertz. And even though it's a nominal 8 ohm speaker, we're measuring 5.81 ohms. We have our acquired waveform, our reference waveform, and the cross correlation of those. So here I have a loudspeaker production test using the fast sweep. I'm using 1/24th octave spacing and similar setup for impedance. So fast sweep 150 Hertz to 15 kilohertz. Let's see how quick this is. I realise we're just about at the end, and if there's any questions, please submit them via the chat window. But here, loudspeaker production test again, same results, but with the fast sweep, we get rub and buzz loudness. We don't get our rub and buzz peak ratio and crest factor. And we do get our high order harmonic distortion. Impedance, phase, partial till small, again the acquired waveform, reference waveform, and cross correlation. And very quickly, I will show the impedance till small, and all of this is, I haven't had to change any connections. I'm using the 517, as I said, power amplifier output, which has a 4-wire Kelvin connection, and which I'll leave that at 20 kilohertz. Just doing this at 100 millivolts out. And we have our till small parameters, and for the standard model fit, we get these additional results. If I change it to LR2, we now get these R2L2 results populated, and these are important, as we said, for loudspeaker designers designing enclosures, etc. We also get different impedance results, also useful for those designers. So if we have any questions, please submit them by the chat.
Yes, I can actually tell you that some of you have actually asked if this webinar is recorded, and the answer is yes. And the recording will also be available. We will let you know probably in the beginning of next week. Then it's available for download. The slides for this webinar will also be available, and again, it will be in the beginning of next week. And then, James, we have a few questions coming up here, and I will read the questions, and hopefully you are able to answer. Otherwise, we will reply directly to the person that have asked. What types of optimization algorithms are used to estimate the parameters? And I think at this time of the webinar, we were talking about the sweeps, the SERT, and the logarithmic sweep.
So, I'm sorry, could you repeat that? What type of algorithms are?
What type of optimization algorithms are used to estimate the parameters?
We would have to get back on that one, because firstly, I'm not even sure if we're allowed to share that information.
That's okay. And again, there are another questions concerning the optimization procedure. Are the optimization procedures for estimating parameters depend on selected excitation functions If so, what are the preferred for each excitation function?
So all of the measurements we've done today are either log chirp or fast sweep. So it's a step frequency sweep. You can use a noise source, and we do support measurements with noise, but not these specific measurements. So we can do, say, transfer function using pink noise, white noise, or the IEC defined noise sources. But the main purpose of this webinar was to show the ease of use for loudspeaker measurements using our acoustic analyzer, and specifically mostly the default measurements, which was the loudspeaker production test. And as I mentioned, you get very similar results in loudspeaker production test that you would with acoustic response and impedance till small, but you only get partial impedance till small. So it's not really for design, but it's great for production and verification.
Okay.
Hopefully that's answered that question.
Let's hope so. And then there's another question here. Can we use electrical measurements to know the rub and buzz?
Can we use electrical measurements? I think it would have to be, I'm just thinking whether a mechanical malfunction or a rub and buzz artifact would affect the impedance. And if something was really rubbing quite badly, I would say that it would affect that impedance measurement because it would have some resistance to the cone moving. I don't think any loose particles do that, so I don't really see how you could measure that electrically. The rub and buzz really is presented as an audible artifact due to those defects. And for example, how could you measure a rattling door panel electrically? I don't see how that would be possible.
Okay, that's another one also concerning rub and buzz, and the question is rub and buzz only in software version 6.1?
No, rub and buzz has been there for a while, but that would be the rub and buzz peak ratio and crest factor that I explained with the high pass tracking filter, and then the taking the residual from the high order harmonics and producing the peak ratio and the crest factor. The high order harmonic distortion, the rub and buzz loudness, and zone track are only available in 6.1 and later.
Okay, good. And then there's another one. Can we do all the measurements we have talked about in electrical way?
I think we've just answered that.
Yeah, I think so. I think so.
Yeah. So the impedance till small is an electrical measurement. So you're measuring the voltage across the driver and the voltage across a sense resistor and plotting the impedance and obtaining the teal small parameters from that. Everything else was acoustic and was acquired through the measurement microphone.
Yes, yes, yes. And then there's a last one. I'm not quite sure what. It's only asking a step response. So yes, we support step response as well.
Yes, and as I mentioned, you could use an old-fashioned step frequency sweep, but it is very slow.
Yeah.
But there's nothing to stop you doing that.
Okay, I think it looks like for me that we have actually answered all questions.
Okay.
We have answered some of the questions directly to you, and others have been answered here live.
Okay. And anything that we haven't answered, we'll get back to. And if you have any questions on this or anything else, you can submit a question to either techsupport@ap.com or support@grassacoustics.com. And thank you all for attending. And I'll now end this webinar and hope to see your questions soon.
Yes, thank you for participating here this morning.